Hey guys and girls, so in today's video I'm going to be showing you how to do greedy mesh. Greedy mesh is a technique of merging voxels together in order to reduce part count. So if we look at this chunk on the left, we can see that there are 4 grey parts to represent the 4 grey voxels. But if we look to the one in the center, we can see that these 4 parts were merged on the z-axis to be reduced from 4 parts down to 2 parts. And if we look at this one on the right, we can see that now it's been further reduced from 2 parts down to 1 part. And if we look in workspace and in this folder 0, and if I select all children, we can see that this chunk has a total of 256 parts. And if we check the center chunk, we can see that the part count has been reduced to 178. And if we check the final chunk, we can see that the part count was reduced to 163. So to get started, let's first create a script inside of server-script service and delete this line here. And the first thing I'm going to do is create a table of colors. So local colors equals, and I have 3 colors, one being a green color to represent grass, one being a brown color to represent dirt, and one being a grey color to represent rock. Now I'm going to create a table called blocks, and I'm going to loop from 1 to 16, and I'm also going to loop from 1 to 16 once again. I'm now going to use the X and Z coordinates to store block IDs into the blocks table. So to do this, I'm going to say blocks and use the X value as the key equals an empty table, and then I'm going to say blocks, and I'm going to use X and Z equals math.random, and I'm going to select a random number between 1 and 3, and this is also the same amount of numbers I have as colors. So it's going to, the ID is going to represent a color in this colors table. Now that I've set the IDs for the blocks, let's loop again through the axes and spawn the parts. So for X equals 1 to 16, do. For Z equals 1 to 16, do. And first I'm going to create the part. I'm going to position the part using the X and Z as the axes, and I'm going to set the size of the part. I'm going to slightly reduce the size from 1 to 0.9 so that we can see the edges of the parts. I'm going to set the color of the part using the colors table and the block ID to select the correct color. And I'm going to set the top surface to be smooth. I'm going to anchor the part, and then I'm going to parent the part in the workspace. If we play the game, we should see that we have 16 parts spawn along the x-axis and 16 parts spawn along the z-axis, and they have a random color. Now we need to try to work out which blocks we can merge so that we can optimize our voxels. So the first thing I'm going to do is create a table, and in this table I'm going to store the width and height of every block. So I'm first going to loop through every block and store the values of 1 and 1 as the width and height. So we can imagine this as being something like this. I'm now going to loop through the voxels again, but this time I'm going to start at the second voxel on the z-axis, and I'm going to look at the voxel below me, and I'm going to ask, does this voxel have the same ID number as this voxel? And if they do have the same ID number, I'm going to add the height from the voxel underneath and the height of the current voxel. So 1 plus 1 equals 2. And then I'm going to erase this size data from this voxel. I'm then going to move on to the next voxel and do the same checks again. So I'm going to say, does the ID number of this voxel have the same ID number of this voxel? And because they don't, I'm going to simply skip this voxel and move on to the next voxel and do the check once again. So does this voxel have the same ID number as this voxel? And because they don't, I'm going to skip to this voxel, and then I'm going to say, does this voxel have the same ID number of this voxel? And because they do, I'm going to add the heights together. So 1 plus 1 equals 2. And I'm then going to erase the voxel underneath. And from here, we move down to the second voxel on the z-axis, and we continue checking. So does this voxel have the same ID as this voxel? It doesn't. We go up. It does. We add the heights together. This one gets erased. We check this one. It's different. We check this one. They're the same. So we add the heights. And we come down here to this one here. We check that is this the same with this? It's not. Then we check this one over here. Is it the same as this? It is. So we add the heights. So 1 plus 1 equals 2. We erase this. Then we move up. We say, is this the same with this? And it is. So we add the heights. So this time it will be 2 plus 1, which equals 3. And we erase this. Then we move up again. And we check this with this. Are they the same IDs? Which they are. So 3 plus 1 would equal 4. And then we erase this. So once we've finished looping through every voxel, we should have only these values remaining in our size table. And then we can use these values to generate our chunk. So now let's create the table to store our sizes. So I'm going to say local sizes equals table, and I'm also going to create a table within a table. Sizes x equals table, and also down here I'm going to say sizes x z equals. Now, unlike blocks where we store the ID number, for the sizes I'm going to store a table with a x and z value to store the width and height. So I'm going to create a table and have a key called x and have it set to width 1, and have a z key and also have that set to 1. So now that every voxel has a size of 1 and 1, now let's loop through the voxels once again and merge the voxels that have the same ID. So I'm going to say for x equals 1 to 16 and for z equals 1 to 16. But if you remember, we started on the second z, not the bottom number 1. So what I'm going to do is change this 1 to a 2 so that we start on the second voxel. Now what I'm going to do is check the ID with the previous z-axis ID to see if they're different or the same. So what I'm going to do is say if block, and using the x and z values as the coordinates, is not the same to the block ID but with the z negative 1, then continue. So if this ID number is not the same as this ID number, we're going to continue, which means to skip this loop and move on to the next value on the z-axis. But if they are the same IDs, what I'm going to do is increment the z value on the size. So I'm going to say size using the x and z as the coordinates, dot z, which is this value key here, plus equals, and I'm going to take the z value from the previous size. So z -1, which is the voxel underneath, and take the z value. So I'm incrementing this z value from with the z value of the voxel underneath, and then I'm setting the voxel underneath to have a value of 0, which is like erasing that voxel. So instead of blindly creating parts from 1 to 16, let's now use our size table to generate the parts. So what I'm going to do is say for x column in pairs. We're not going to use I pairs because there may be blanks within the size table because we've erased some. And then I'm going to say sizes do, and then we're going to loop through the column. So I'm going to say for z size in pairs column do, and now I'm going to copy and paste the part creation part from this loop into our new loop and delete this part here. And I need to make a few changes. The first change I need to make is, instead of using 0.9 as the width and height, I'm going to use the size. So this is going to be size.x, and this is going to be size.z, and in order to see the edges, I'm going to subtract the size by 0.1, so -0.1, and do the same for the z size, so -0.1. I'm also going to subtract the position by half of the size, so I'm going to say x negative size.x divided by 2, and the same for the z size, so size.z divided by 2. So if I play the game again, we should now see that our voxels are being merged along the z axes. So now let's try to merge along the x-axis, and this is done almost identically how we did it for the z-axis. So we start on the second x-axis, and we first check to make sure that there is size data on this voxel. If there is size data, we check the voxel behind to make sure there's size data. If there's no size data on this voxel, we skip. So we move forward, and we can see this size data, and we check that there's size data on the previous voxel. Then we check to make sure they have the same ID, which they are, and then we also check to make sure they have the same height. So we can see that this has a height of 1, and this also has a height of 1, so we can merge these together. So we add the width with this width, so now the width here would be 2, and we erase this size data. Then we move to the next voxel. We check to make sure that this has size data and the one previously has size data. We check to see that the height is the same. We can see they both have a height of 1. And then we add the width with this width. So 2 plus 1 equals 3, and then we erase this size data. Now instead of looping blindly through every voxel like we did for the z-axis, it would be more efficient to use pairs to loop through only the voxels that have a size set to it. So we could start on the second voxel on the x-axis and then use pairs to loop through all the sizes on the z-axis. So when we use pairs, the order is undefined, so we're not sure what size we will read first, but the order is not important, because if, let's say we start with this size, we would check the one behind to make sure there's a size data, which there is. Then we would check the height, where this has a height of 1 and this has a height of 2, so we would skip this voxel. Then we would check the next voxel, which would either be this one or this one. We would check the one behind. It doesn't have no voxel data, so it will be skipped. Then if we checked this one, we'll check the one behind, and they both have a height of 2, so they both have the same height. We then check the ID. They both have the same ID. And then we add the width with the width on here, so 1 plus 1 equals 2, so this would now be equal to 2. And then we erase the height, for the size from this voxel. And once we've finished checking the x-axis, we should have a size table that looks like this. So now let's do what I just said in Lua. So the first thing we need to do is loop along the x-axis. And if you remember correctly, we started from the second x-axis. So instead of starting at 1, we change this to 2. And then we're going to loop through every size value inside of this x-axis. So to do this is the same way we did it here for generating the parts. But the only difference is we change this column to say sizes.x. So this is going to loop through every size along the z-axis, and then the first thing we're going to check is to make sure that the size to the left exists. So I'm going to say if I copy this, if I copy this, and if I say x negative 1, so the one to the left, equals nil. Let's not forget the if equals nil, then continue end. And then the next thing I'm going to check is to make sure that this z value is the same with this size and the size to the left. So what I'm going to say is if size.z is not equal to the one to the left dot z, then continue. And our final check is to make sure that the IDs are the same. So we can copy this from when we checked it on the z value, and we only have to change this -1 and move it to the x, so it's x -1. And once we've done that, we now need to do this part, but instead of it being on the z, we have to change the x, meaning the width. So I'm going to say size.x plus equals, and I'm going to get the size from the one to the left, dot x, and then I'm going to set this to nil, equals nil. And if we play the game once again, we should now see that our voxels are getting merged along the x-axis. So we can see that this block here was merged together, and this one here was also merged together. And we can see that all these were merged together. If you wanted to have greedy mesh in all three axes, What you would do is pretty much the same thing what we did for the X and Z axes. So if we imagine this was another layer of blocks above, you would simply start from the second from bottom, check the one underneath. If the X and Z are the same, you would increment the Y size and add it to the one above. And you would keep doing the same thing, just the same way we did it for the X and Z axes. Now let's talk about the downsides to Greedy Mesh. While Greedy Mesh will increase your frame rate due to having less parts that need to be rendered, Greedy Mesh will make chunks take a lot longer to load due to the complexities of calculating the size of each voxels. While this should not be too much of a problem for doing Greedy Mesh in 2 axes, because 16 times 16 is only 256 blocks that we need to calculate Greedy Mesh for. But if you have a chunk size of 16 times 16 and a height of 256, now we must do Greedy Mesh on 65,536 blocks, and this can take a little while to do. The next problem to Greedy Mesh is adding and removing blocks. So if, for instance, let's say I would like to delete this grey block over here, I would have to destroy this entire part and increase the width of this block to come over here. And I personally do not know an optimal way of calculating this. But if you only have Greedy Mesh on a single axis, then it should not be too difficult to resize the parts in order to add and remove blocks. Another option is to just simply recalculate the entire chunk from scratch when a block is added or removed, and this should not be too bad on a 16 by 16 chunk. Thank you for watching the video, and if you have any questions, feel free to leave a comment down below.